Hi guys, today we will discuss the Rolle's theorem. So, according to this Rolle's theorem, we have a function. It's a real valued function, right? Fx. So, we will check this or we will verify Rolle's theorem on closed interval a comma b. So, we have a function fx. It's a real valued function, and we want to verify this on closed interval a comma b. So there are three conditions. Number one, this function should be continuous. On closed interval ab, means a and b both terminals should be included. And the second condition, function fx, we will obtain its first derivative. So the function should be differentiable. At open interval ab, means except these terminal values a and b. In between values it should be differentiable. And third is fa should be numerically equal to f. So these are the terminal values. So we put value a in this function, we get fa, and second value, it's a second terminal, rightmost terminal, we put x equals to b in this function and we get fb, and the both values should be equal, right? And then there exists a real number c in the open interval a comma b such that f dash c should be 0. Okay, so we want to collect a value c which should be between a and b, and for this value the first derivative of function should be 0, or you can say f dash c equals to 0. According to this, on solving this condition for c, for the value of c, and we will collect the value of c, and that value of c should lie between a and b. So if it lies between a and b, then the function will be verified as a Rolle's theorem at closed interval ab. So the Rolle's theorem will be verified at closed interval ab. So the function fx verify this theorem at interval ab, right? There exists a real number, real value c in the open interval ab. Remember this open interval, c should be in open interval ab, yani excluding a and b, if such that f dash c equals to 0. So for this value it is meanwhile between a and b. For this it should satisfy this condition: the first derivative of the given function at this value should be 0. So we will collect that value, and those values which lie between a and b will verify this condition. Function fx is x cube minus 6x square plus 11x minus 6. and the interval on which we should check this verification of Rolle's theorem, that given interval is one comma 3, close interval. So first, being fx being a polynomial, so it is continuous at every point between 1 and 3, or in close interval 1 comma 3. So every point of this interval the function will be continuous because it is polynomial. And the second condition, f dash x is 3x square minus 12x plus 11. So it is clear, we can observe this is also a polynomial, and it is all values between 1 and 3, it has value, it is differentiable. So the function fx will be differentiable at open interval a comma b. Remember this is open interval and this is close interval, so you can say 1 comma 3. Now third is the proving condition. First we will collect the value of f1, yani ke means we want to collect the value of function at x equals to 1. So put x as 1 in this given function, so it will be 1 cube minus 6 into 1 square plus 11 into 1 minus 6. So it is 1 and this is 11, this becomes 12, and this is minus 6 and minus 6 is again 12. So we get the value 0. And same way we will collect the value of function at 3. So put this value in the function, so it is 3 cube minus 6 into 3 square plus 11 into 3 minus 6, again it is 27 and it is 33, so it is 60, and this is 6 into 9 54 minus 6, again it is 60. So 60 minus 60, it is 0. It means f1 equals to f3. So all the three conditions satisfy this function, on this function at close interval. That is clear, there should be some value at which the first derivative of given function should be 0. So we will collect that value c. So for the value of c, first we will get f dash c. So we will put the value c on place x. So we get 3c square minus 12c plus 11, and we put it as 0, and we will simplify this. So c equals to minus 12 plus minus under root, it is minus 12 square minus 4 into 3 into 11 divided by 2 into 3. So we will use the quadratic formula to solve this, and we will get the value, that is 2 plus minus 1 over root 3. So both the values like lie between 1 and 3. So the Rolle's theorem is verified on these values. Now for the verification of Rolle's theorem, we have a function fx equals to x minus 1 multiplied with x minus 2 and again x minus 3, and the interval on which we will check this, we will collect the value of c in this interval 1 comma 3. So we have this, as we know this, on simplifying this function we get x cube minus 6x square plus 11x minus 6. So this is the expression, and this is a polynomial function, and every polynomial function is continuous. Fx should be continuous at close interval 1 comma 3, means all values between 1 and 3 including these extreme values 1 and 3. And the second condition is f dash x is 3x square minus 12x plus 11. So it is differentiable on each value between 1 and 3. So the function, because the values, all values exist between these existing values between 1 and 3, so fx will be differentiable at open interval 1 comma 3, means excluding 1 and 3. And third, we will collect the value of f1, means the value of function at x equals to 1. So put it in this. So x minus 1, so when you place 1 minus 1, it will be 0, and when you multiply all these, 1 minus 1, 1 minus 2 and 1 minus 3, so it is 0. When you multiply with 0, you will get 0. And similarly we will obtain the value of f3. So put x as 3, so it will be 3 minus 1, 3 minus 2 and 3 minus 3. Again 3 minus 3 is 0, so when you multiply with 0, result will be 0. So f1 equals to f3. So all the conditions for Rolle's theorem, these are satisfied. That means there should be some value between 1 and 3 for which f dash c equals to 0. So for getting the value of c, first we will collect f dash c. So we put x as c in this first derivative. We get 3c square minus 12c plus 11, and according to condition for Rolle's, it should be 0. So for this condition we will solve the value of c, that is c equals to minus of minus 12 plus minus under root minus 12 square minus 4 into 3 into 11. We are using the quadratic formula, and 2 into 3. So after solving this we get 1 plus minus 1 over root 3. So both the values 1 plus 1 over root 3 and 1 minus 1 over root 3 both lie between 1 and 3. So for open interval 1 comma 3, So Rolle's theorem is verified for both values of C. Fx equals to x minus 2 power 4 and x minus 3 power 3 on the interval, close interval 2 comma 3. So this is the polynomial function. To being a polynomial function, function fx will be continuous at close interval 2 comma 3. F dash x. So when you get the first derivative, so you use the formula of product rule with chain rule. So you will get 4 x minus 2 cube, x minus 3 cube as it is, plus x minus 2 whole power 4, and the derivative of this is 3 into x minus 3 square. So you can say it is x minus 2 cube and x minus 3 square. These are common. So it will be 4 into x minus 3 plus x minus 2. This is. So it will be x minus 2 cube, x minus 3 square, and this is 4x, and 3x is 7x, and this is minus 12 and minus 6 is 18. So this is f dash x. So third condition is, according to this given function fx is differentiable at open interval 2 comma 3. So the third condition that should be satisfied, we will collect the value of f2, means we will put the value of x2 in this given function. So it is 2 minus 2 power 4 and 2 minus 3 3. So it is 0, and when you multiply this you get 0. And the value of f3, it is 3 minus 2 power 4, and this is 3 minus 3 power 3, and it is 0. So multiply this is 0. So f2 equals to f3. So all the three conditions for Rolle's theorem are satisfied. So these are satisfied. So if it is so, then there should be some value c between 2 and 3, open interval 2 and 3, for which the first derivative will be 0. So x as c, in this first derivative we get f dash c as c minus 2 cube, c minus 3 square, and 3c minus 18. It should be 0. F dash c equals to 0. So according to this condition, we get the three values of c. C equals to 2, c equals to 3, or c equals to 18 by 3, means 18 by, sorry, this is 7. So it will be 18 by 7. So you get 2 point, this is 2 and 4 by 7. It means between 2 and 3. So these are the extreme values, and the value of C should between 2 and 3 except 2 and 3. So the value of C which lie between 2 and 3, that is 2, 4 by 7. So C is 2, 4 by 7 lie between 2, 3 open interval. So Rolle's theorem is verified for this value. Verify the Rolle's theorem at interval, given interval is -1, 1. So for the Rolle's theorem, there should be 3 conditions should be satisfied. Number 1, this is a function, so fx is continuous for closed interval -1, 1. And second statement, fx is differentiable for open interval -1 and 1, and the derivative of this f dash x is 1 over under root 1 minus x square, and it is minus 2x. So cancel out this, we get minus x over under root 1 minus x square. This is the derivative. And third condition is find the values of f minus 1. So put it in the given function. So 1 minus minus 1 square, so it is 1 minus 1, it will be 0. And f1, that is 1 minus 1 square, so it is 1 minus 1, again it is 0. So both the values of the interval are equal, so conditions are satisfied. So we can search for value of C between -1 and 1, for which the first derivative of this function should be 0. So put x as C in the first derivative of function fx is f dash x is this, so put C, it is minus C over under root 1 minus C square. So it should be 0. So when you put this, we get C equals to 0. This comes on this side and becomes 0. So C is 0. So C equals to 0 is the value which lie between -1 and 1. So the given function, on this given function, the Rolle's theorem is verified at C equals to 0. Given function for the verification of Rolle's theorem is x minus a to the power m, x minus b to the power n for interval, close interval a comma b, where m and n are positive integers. So being a polynomial, given function is continuous at close interval a comma b. Similarly, fx is differentiable at open interval a comma b. And third step is put these intervals in this function. So we will collect the value of fa. So it will be a minus a power m, a minus b power n. So a minus a is 0. On multiplication, finally we get 0. fb, it will be b minus a to the power m and b minus b to the power n. So b minus b is 0. On multiplication, finally we get 0. So fa equals to fb. So all the three conditions are satisfied. So conditions are satisfied for Rolle's theorem. Now we will get the value of c, for which the first derivative of fx should be 0. So differentiate this. F dash x is m x minus a power m minus 1 x minus b as it is. We are using product formula on this function, plus x minus a to the power m as it is, first function as it is. The derivative of second function will be this. So when we extract x minus a power m minus 1 x minus b power n minus 1, so we get m x minus b plus n x minus a. So it will be x minus a power m minus 1 n minus 1, and this is mx plus nx, and this is minus mb minus na. So you can say x minus a power m minus 1 x minus b power n minus 1. So m plus n x minus mb plus na. So this is f dash x. So we want to collect the value of c, for which this function should be 0. So we have f dash x is x minus a power m minus 1 x minus b power n minus 1, and this is m plus n x minus mb plus na. So put x as c, so this becomes f dash c is c minus a whole power m minus 1 c minus b power n minus 1, and there is m plus n c minus mb plus na equals to 0. So these are the factors for which the result is 0. So values of c which are obtained as a, c as b, and c as mb plus na over m plus n. So these are the extreme values of the interval, but this value lie between these two numbers. So c equals to mb plus na over m plus n, for which the f dash c is 0. This lie between a and b. Means for this value Rolle's theorem is verified.